Thank you for the introduction and welcome everyone to my talk on JSpecify. So JSpecify is this new standard that was developed over the last 6 years that tries to standardize nullness annotations for Java. And I'll also talk about the checker framework and the nullness checker in that framework. So it allows you to check these annotations statically. How many of you have run into a null pointer exception? Yes. Okay, null pointer exceptions, they are everywhere. They're particularly annoying in Android apps, things where you expect some immediate response and things just crash and you just get a null pointer exception. So Tony Hoare called it his $1 billion mistake, and it's just annoying, and since Tony Hoare introduced it, it's been around. And so many modern programming languages started adding language mechanisms to help you solve this problem. And in Java there are many dozen annotations that help you specify whether something can be null or cannot be null. But there is no standard. So JSpecify aims to standardize different annotations for Java static analysis. So the goal is really broader than just nullness, but nullness is just the first domain that we said that's the most important one to standardize on now. So it's a collaboration of many different companies. So it's Google and Kotlin for obvious reasons. Kotlin is one of these more modern programming languages that have built-in nullness types. And Android uses that. And you still have a large intersection with Java code. And then how do you define what that interface between the two languages is? And so good integration between Java and Kotlin was one of the main goals. But there are many other companies, Meta, Uber, JetBrains behind Kotlin. So JetBrains for the Java sides of things too, and Spring and SonarQube. Did I miss a logo? And ASOP. So ASOP, that's my research group. So that's the optional property type checkers that I work on. So collaboration between all these people. Some of you might have heard of JSR 3 or 5. Have you used a JSR 3 or 5 jar file in one of your builds? I see a few nodding heads, yes. And please interrupt me, and if you have any questions, we can make this as interactive as you want, and I can talk for hours about these topics. So I promise to stop after 45 minutes or so. We'll see. So clear semantics, interoperability are the main goals for JSpecify. And last year, so pretty much 1 year ago, July 17th I think it was, released version 1.0 after really 6 years of work. You can laugh at us that it took us 6 years to standardize 4 annotations, but it was a lot of work to accomplish. There already is good adoption of the artifact, so Google has it easy with the monorepo, and they already use the annotations internally, and things like Guava use the annotations in the newest release. Spring Framework 7 recently announced that they will use it in their upcoming next release, and so they standardized on JSpecify also for the Kotlin interoperability. Chromium, the web browser, is also migrating. And if you look on Maven Central, you see that it's used by 70,000 artifacts already. And so hopefully after this talk, if you haven't used JSpecify yet, you switch away from JSR 3 or 5. So let's quick look at JSR 3 or 5. Many people use that artifact. They shouldn't use the artifact. It's a terrible artifact. It's not a standard. It's JavaX annotation nullness. It has unclear copyright. Nobody really should use that artifact in a commercial product. It's from 2006, and that JSR unfortunately never finished. So it would have been nice if it were finished 20 years ago, but it wasn't. How many of you have thought of this cartoon? No one? I don't believe you. Okay, so that's one honest person. So if you come up with a new standard, you always point to this cartoon and say, hey, why are you inventing another standard? And afterwards you have n+1 standards. The thing is, there is no standard at the moment. So at the moment, there are 0 standards for nullness annotations. And we try to make the first standard. It's not a standard, it's just this informal group of people. So JSpecify is not even a legal company or anything like that. It's really just this conglomerate of people. But it's a lot of Java code behind these people. So it's just a industry standard, I think is the term for that. Okay, so let's maybe have a quick look at the existing annotations. So there are over a dozen different annotations from all these different projects. So NetBeans had one, Spring Framework had nullness, non-null annotations, and there you see there are many, many lines of different aliases for different nullness annotations that we added at some point. Because many people had nullness annotations, and our checker wanted to be compatible with all of them, so we added these aliases, and Android had their own annotations. And so you have multiple dozen different annotations that all kind of express the same thing. And so what we wanted with JSpecify is that we just have one official, semi-official set of annotations. Nullable and non-null should not be very surprising. We need an annotation that says that something can be null, and annotation that something needs to be non-null. Actually, it took a lot of discussion whether we even want that non-null annotation. And for a while we lived without non-null, but for generics it's nice to also have a non-null annotation to make it explicit in certain places. And then the two new ones are null marked and null unmarked. So they mark a scope as what is your default. We wanted to make the transition from current Java to a JSpecify world as smooth as possible. And for that we needed to make a distinction between code that was thinking about nullness and code that is not thinking about nullness. And then if you don't have an annotation, that is normal Java code. You don't know what the nullness of that code is. And then you opt in with this null marked annotation where you say that you marked this code for nullness, you thought about what the nullness is, and then the default is actually non-null. Because non-null is what you usually want for a reference type. It points to a real object. And then you add the nullable annotations in the places where you want to say here the reference can be nullable or can be null.
Good question.
Yes?
So if I want to declare a variable that I want to be non-null, so do I need to annotate it with two annotations? Null markable plus not nullable? Plus not null?
No, so if you mark the enclosing scope as null marked, everything in that scope, in that class, is non-null by default. So yeah, so you annotate your class, your package, your module, and you just say that whole module is null marked, and then you don't need, except for certain generic situations, you don't need any non-null. You can use non-null explicitly without the null marked, but it's really just very verbose, because you probably use a lot of non-null. Yeah. And why do we not have null unmarked? It's sometimes you want to opt in the package. You say this package is null marked, but so that if you add a new class to that package, it's also null marked. So everyone is obligated to fulfill the nullness annotations. But maybe you had a difficult class that you didn't want to annotate. Then you can opt out that particular class, can opt out the tricky method where you say, I don't want to think about this mess at the moment, and you null unmark that component. So null marked, null unmarked gives you this flexibility to opt in your code, make sure that you don't backslide, that you don't add new code that doesn't get annotated correctly, and you still can opt out where you want to say, here it's unclear what the semantic should be, I just don't annotate it, it's unmarked. Okay, that was the 5-minute summary of what JSpecify is. At the moment, we have 4 annotations, but the goal for JSpecify is that we add other domains. The first one is check return value. I forgot what the new name is. So something where you say that you want to make sure that users of an API need to use that return value. So that's probably the next domain that we work on standardizing, because it's, again, in Java land, error-prone, has a similar semantics. Kotlin want to add that, so it would be nice to clearly define what the semantics are and standardize on these annotations. And this is an open group, so if you have other suggestions for what are common problems, common annotations that you would want to see standardized, reach out to the JSpecify organization. Well, GitHub organization. Okay, so that was the main takeaway for JSpecify. I'll talk now a little bit about pluggable type systems, so how you can enforce this. And it depends on how interested you are in that. So if you're interested in type system, I'll talk a lot about type system. If not so much, we can talk more about a few JSpecify problems or situations. And I try to weave them together, and we'll see when you kick me out. So what is the idea of optional type systems? Java is nicely statically typed. We cannot assign strings to an integer variable. We don't want that because we don't want field not found, method not understood errors. So that's one nice guarantee. If you don't have any unchecked warnings in your code, you don't run into these problems at runtime. But there are many problems that still happen at runtime. So here the first one, system.console.readline. What could happen here?
Console is null.
Console is null, exactly. So you have to read the Java doc of all your methods and see, okay, under which conditions could that thing return null. You wrote all your test cases, you always tested it on the command line, so you always had a console attached. Your client double clicks on it, it runs in headless mode, suddenly system.console returns null. And Java, the language, doesn't force you to check for null, so you just run into null pointer exceptions. There are many, so let's try whether this demo works. Where's my mouse? Here. So here we have a live demo of this Checker framework, and we have this code where we use system.console, and from the static analysis you get this error message that here you dereference something that's nullable. And so what you can do is that you check this first. And so you want to put this, what is it, java.io.console C is equal to this. Is it Java IO console? Yeah, so now I know that it's C. Then I write if C not null, I do this, and else and now it doesn't complain. So the point is that these static analyses can be very powerful and make it very easy to check your code for correctness, even without any extra annotations in your code. So you didn't need to annotate anything in this with a nullable annotation. The type check is just clever enough to say, okay, this is a local variable, so allow an arbitrary type. And then you check for null, and it's clever enough to refine that type. It knows in the then branch C is definitely non-null. If I try to dereference C down here, I will get the same error again, because in the else branch C is null again. C, and we get that same dereference of nullable. So the goal of these pluggable type systems is to allow you to enforce these additional properties at compile time at a minimal cost. So you have compile time overhead, but no runtime overhead. And it makes sure that you use your references correctly and without a lot of overhead. And now I showed you the Checker framework. How many of you, has anyone heard of the Checker framework? I see? Well, my students don't. I saw one hand. Great. So the Checker framework is this framework for nullness checking and many other type systems. And we had a certain interpretation that for all source code, we assume that it's non-null by default. And I'll talk a little bit about how that is incompatible with what we wanted for JSpecify, and why in JSpecify we have this null marked and null unmarked. Any questions so far? No. Okay. Okay. Quick motivation. Why do we need annotations at all? We need annotations because we need a specification. Without a specification, we cannot point out where the problem in our code is. So here we have some code. We transform that input. We have an invocation with null. Is the fault that we directly dereference in that operation, or is the fault that we pass null as an argument? We don't know. We need some specification. And then, so far, you can only just use Javadoc comments and write in English. Okay, do you allow null or do you not allow null? And we want to formalize that. And that's what these annotations are for. We can now precisely specify, is that parameter expected to be non-null? Then it's okay to directly dereference it, because it's some internal private method. You don't need to be defensive. It's non-null, and you trust that. And then the invocation with null is to blame. Or the alternative is that the parameter should be nullable, and then the implementation of the method is wrong. And you should change the implementation, add that guard to make sure that it's actually non-null when you dereference it. So the goal for JSpecify is pretty much to provide that specification language to allow you to say you are nullable, or you are in the null-marked world where everything is non-null by default. So JSpecify is the specification language, but you still need some tool that interprets it. JSpecify does not provide a type checker. It's really just an artifact for annotations. And so you can have that dependency, and you say it's nullable, you say it's null marked. If you don't check it, you don't get any guarantees out of it. It's just the specification language. So then you have multiple options for what tools to use to enforce that the annotations are correct. Has anyone heard of Nullaway? Nobody. Oh. So Nullaway is another very popular tool for enforcing null correctness. That's why Uber was in JSpecify. It's a tool developed by Uber to ensure null correctness. They use the checker framework nullness annotations, and now they also support the JSpecify standard. And so you have Nullaway, you have the checker framework, you have JetBrains has built-in analyses, and you have all these different tools that help you ensure correctness. And Sonatype was one too. So the goal is that we have these specifications, you write your type qualifiers, and then you enforce the correctness of your type qualifiers at compile time. The checker framework is an annotation processor, so it just plugs into the normal Java compilation, and then at compile time you get error messages about any misuses that you might have in your code. Quick overview, normal type checking. We have a source code, we have the compiler that looks at the source code. Initially maybe you get some errors and warnings. Hopefully it points out useful things. Sometimes in early Java versions you had that stupid pattern where you have an instance off and then you still need to cast it, where you just add the cast just to make the compiler happy. The instance off already made sure that it's the right type. So you fix bugs, or you change the types, add additional casts to make the compiler happy. Once the compiler is happy, you get the executable, but you have all these possible runtime exceptions from the executable. So the idea of these optional or pluggable type systems is that we add this additional loop. The base language needs to be happy. Java needs to be happy, otherwise the additional type systems wouldn't help you. So once Java is happy, we add these additional optional type checkers, and they provide the same feedback. So they say, here you're doing something incorrect, you're dereferencing something, this is bad. And sometimes you have to provide additional specifications. You add annotations, you convince it that the code actually behaves correctly by changing the types in your code. So you have that same loop, and eventually, once the optional type check is happy, you have guaranteed behavior. If your type check is sound, meaning that the implementer of the type system thought about the correctness of the code, you have an actual guarantee that you will never run into null pointer exceptions. You will never run into a security violation. You have all these guarantees about the correctness of your code. The nice thing is you can do these things in parallel. Once the Java compiler is happy, you can run your code. You can ship it to production if you want. And in parallel, you find the annotations, you fix the bugs until you get the guarantee about the correctness. The other nice thing is that you can pick multiple optional type checkers. So not all properties are interesting for everyone. So you pick and choose that you care about SQL injection attacks. You care about tainting for HTML. And you enable just these type checkers for your code. There's a question here?
Yeah, I have a question. I'm just wondering if I understood you correctly. So compiler produces executable. An optional type checker kicks in the runtime or what?
No, it's a compile time.
So it's before the executable gets created, right?
Well, so it's in parallel. If you just invoke the normal Java compiler, you just produce the executable. If you invoke it with an annotation processor, the annotation processor takes that optional type checker loop. And then if the annotation processor doesn't produce any errors, the compiler goes on and produces the executable.
Okay, so like if you do want to use it, then it would prevent to create executable if there's something wrong with the type checker, the type checker detects.
If you make the type errors for the compilation,
Okay.
there is a flag to make them only warnings, and then it would always produce an
So it's
executable.
like in Kotlin there is a concept of a compiler plugin.
Yeah.
It's similar.
It's similar. It's annotation processors is in the name in Java. But in Kotlin, you cannot, if you violate the nullness type system in Kotlin, you never get an executable.
Yeah.
Here, if you just invoke the Java compiler without the annotation processor, you still get the executable. And even if you enable the type system, we have a mode to say just warn about things, don't error.
But it's based on your intention, right? So
Exactly.
basically if you want to skip or if you want to add this type checker, then you can rely on it blocking the
Compilation.
unexpected result.
Exactly, yeah. And it's all at compile time. So it's just compiling your source code. It does not affect what bytecode you get. Well, we'll talk about how it affects the bytecode in a second.
Okay. Thank you.
Hello, I have a question.
Yeah.
So, you mentioned that it will happen in compile time, right? Not during the application startup, like aspects work or something like that.
Exactly. So the annotations have one-time visibility.
Yeah.
So we want that because we want to store the annotations in bytecode. And for some tools that might want to inspect it at runtime, we want it with one-time visibility. So the annotations don't just have source visibility, they have one-time visibility. So maybe there's a tiny overhead.
Actually later, right? If we want to just to write some additional aspect to that, to I don't know, to process them somehow.
Exactly. So you could inspect the method, look at the return type, and see the annotation
So
there.
they will be in the bytecode somehow. Okay.
They will be in the bytecode and in reflection, in runtime reflection.
Like in metaspace, like stored with the class probably, right?
So there are three visibilities. There's source visibility, where it's not even stored in bytecode. There's bytecode visibility, where it's in bytecode.
Yep.
And then there's one-time visibility, where it's in bytecode, and then when the JVM loads the class file, it also represents it in reflection.
Yeah.
And so it's one-time visibility, so if you want to reflectively look at a method, you still see the annotations.
Okay.
But there's no one-time checking of the annotations. It's really just the meta information that you have.
What you can implement. I don't know how
Yeah.
how is it possible to implement better than optional API is implemented for runtime.
Okay?
But for compile time, yeah, that looks awesome.
Okay, cool. Okay, so that is the basic idea of how we always sell optional type checking. So if you saw my grants to my talks on this topic, we present optional type checking, gives you this additional loop. Why do we like type systems? They help you find bugs in program. And if you have a sound type system, you actually have a guarantee about the absence of certain errors in the code. But it helps tremendously just having the type system when you initially write code. Adding it after the fact is very painful because you make all these implicit assumptions about where something can be null, and it can be very tricky to add that afterwards. And so just the documentation benefit of having a precise language about something can be null or non-null instead of having vague Java doc is very helpful. For some other type systems, it might be good for helping the compiler, aiding other static analyses and things like that. The two negatives: must write types. You need to provide a specification. Without specification, how do you know what your desired behavior is? On the research side, we work on type inference. So how can you look at the source code and try to find the correct annotations automatically? The second problem with static type systems, if they aim to be sound, they usually have some false positives. So they produce errors in situations where you say, but it's clear that this should be non-null. The checker framework has lots of logic to help you minimize the false positives. So it has lots of sound heuristics by default, implemented logic for many tricky APIs. But there's always the possibility that you have some tricky logic about when something is non-null, and then you have a warning and you can suppress the warning. So we have lots of command line flags that allow you to suppress warnings, say I don't care about the GUI package, just don't type check that package at all. And so you can configure what parts of your code you want to trust.
Does it work with suppress warning annotation or just some custom annotations?
Both.
Okay.
So we have the standard suppress warnings annotations where you want to modify the code, but if you want to ignore a whole package, we have a command line flag and you just say, okay, don't look at that package. Okay, and what I talked about is the ASAP version of this checker framework that plugs into the Java compiler, so it's the OpenJDK Java compiler, not the Eclipse Java compiler, and works on that AST and adds all the type checking to the compilation. And then depending on how you run it, you get errors or you get warnings that abort your compilation. We have instructions, we have a very, very large manual with examples for how to configure it in Gradle and all the different build system, living and dead. Eclipse IntelliJ, it's a standard annotation processor, so as long as you can configure your IDE to run an annotation processor, you get the standard error messages and it's super easy to integrate. And I already showed you the live demo where we have this website where we can play with a bunch of the other type systems just to see very quickly how things behave. Okay, so let's get back to nullness. We have nullable and non-null. Nullable is the supertype. Nullable contains the null value too. Non-null is the smaller type. It's the subtype. So we have these additional meta annotations, and they're so-called type use annotations. So Java 8 added a mechanism to allow you to annotate all type uses in your Java code. Previously, with Java 5, annotations only supported declarations. So you could only have a class declaration, method declaration, parameter declaration, all these places you could have annotations. That's not good enough for a type system. For a type system, you want to be able, every type that appears in your code, that you can specify a non-null list of nullable strings. So that's two type users, first the list and then the type argument. The checker framework uses non-null as the default. Every time you compile Java source code, you assume that you want the type system enabled for that source code, so we enable non-null by default. With JSpecify, we change that behavior. So with JSpecify, you need to opt in to non-null as the default using that null marked annotation. The type system is relatively easy. We have 20 or so rules, places where the JVM specifies that here I will raise a null pointer exception. For each of these places in a visitor for the abstract syntax tree, we say if you dereference an expression and access a field, that expression needs to be non-null. If you invoke a method, if you throw something, all these places where the JVM specifies it throws a null pointer exception, we statically say this type has to be non-null. So if you try to dereference, so in the example we saw this method invocation, if you try to invoke readline on something that's nullable, you get an error at compile time. So it's 20 or so places where the JVM says it throws a null pointer exception. For each one of these, we say in the abstract syntax tree, that expression, that type has to be non-null. Okay, so now this is the nice academic picture. In reality, you have the problem that you need to represent your types in bytecode. So what you actually get is different bytecode when you run the optional type checker. And that bytecode contains the explicit annotations to make it explicit what assumptions you had for your source code. Because you had your source code, you run the nullness checker on it, you want to make sure that you document that you assumed that this field is non-null. The only way to make that explicit in bytecode is if you add that annotation to your bytecode. So you get different bytecode out of running it with an optional type checker to make these assumptions explicit in your bytecode. Now you have users of your code. So now your compiler takes these bytecode inputs. It might take normal bytecode from the normal Java compiler without these annotations, or it might take your bytecode that the nullness checker produced. So you need to make different assumptions for them. One, you see that it's annotated as non-null. You can rely on that. Or you don't see the annotations, and then you treat it as something that might be nullable. And we didn't like that model. So at the moment, you have your bytecode. If you run it through JavaC, nothing happens. You just have the representation of your source code in bytecode. If you enable the normal checker framework nullness checker, it makes these annotations explicit. As I said, our assumption is that everything is non-null by default, even without the class annotation. So in the bytecode, suddenly this field has a non-null annotation, making explicit that you type checked it under the assumption that the field is non-null. And the same with the parameter and the return type, we make the nullness annotations explicit. Yeah?
So what the previous slide showing like Java C without, so like this Java check, it's a different like compiler?
So it's just with the class path added. So it's just a macro, a shell macro that we have to add the class path for the checker framework.
So technically it's just like an annotation processor,
Yeah.
like the same Java C.
Yeah.
But then second question, how do you modify the source code to include these non-null annotations? Is it like some long black magic, or this is like all public APIs?
It's not public API. So it's not Lombok magic, because Lombok also wants to work for the Eclipse compiler, so it has multiple backends and lots of black magic there. We just want to work with the OpenJDK compiler. The problem is that the public API for the compiler only goes to the declaration level. So for the method bodies, there is no standardized API. So we have to use the compiler internal AST nodes to get to the method bodies.
So I would need like add opens.
Exactly. So and that's the thing that this Java check macro does. So it just adds the required Java files to the class path, adds the add opens and whatever the other one is. Yeah. Yeah?
Yeah, previous slide, please. Previous slide.
Previous.
The one with the library.
This one?
I'm,
Yeah.
I'm trying to understand here for the compiler, it gets the source code. This is totally clear, but does it get an executable or an executable annotation as an input to it?
So if you have a dependency on the library, so the Java compiler just takes source files and class files as input, right? So with executable, I mean class files, bytecode files.
Okay.
And so you have separate compilation. You compiled class A.
Jar files or the executable.
Yeah. So the class file, the jar file of that first compilation,
Okay.
and that's input to your second compilation, right?
Okay, so the event is I have, it's not the executable of the same source.
No, not, yeah, good point, yeah. So the executable here is two different sources. Yeah, that's not clear. So yeah, this is the executable from this source file. The other one is executable from the standard library.
Oh, okay.
So some precompiled source code and some library that you also type check with the nullness checker. And that code has annotations in it. That's a great point. I should change that. Yep. Other questions? No? Okay. Okay. So we added the nullness annotations. We are type system geeks. So we added actually 3 hierarchies. So we added nullness. We have a key for hierarchy to ensure the correctness of map keys, where you also have, if a map is from key to values and the values are non-null, you can still get null back. because maybe the key is not in the map. And so we have a separate type system that keeps track of that. And object initialization is another very tricky thing where you run into null pointer exceptions, because your object is still under initialization and you access a field that you think is non-null, but it wasn't initialized yet. So we have this third hierarchy that keeps track of initialization. So your bytecode adds all these annotations. We need that to make sure that you know under which assumptions you type checked your code, but we have different bytecode. So this I just said. So the current behavior is nice because we don't need extra annotations. We have annotations to influence defaults, but our default behavior is that we have a meaningful default, everything is non-null by default, and that works nice and easy. All source code is considered annotated and is checked. That's easy for usability because you don't need this extra step to opt in. You type check a Java file, you get feedback about that Java file. So from the usability, what we did in the checker framework made sense. But it had serious disadvantages that we didn't like in JSpecify. You have this problem with the build artifacts. And so you have separate artifacts if you run type checking or you don't run type checking. So it depends. You always need to run the checker framework to get the artifact that you want. We wanted that for JSpecify. You can just use the normal Java compiler and you get bytecode that represents that information. It does not depend on an additional static analysis tools. In particular, it means that you're on the critical path for your build because that artifact needs to run through the type checker first, and you also need to enable all type checkers at the same time because each one, if you run them in two separate processes, they create two different class files. And how do you merge them? So with JSpecify, we added this null marked annotation. So now you need to make it explicit in your source code that you live in this null marked world, that you make these nullness explicit. Nothing interesting happens with the bytecode anymore. Whether you run normal Java or here I called it JSpecify nullness, so a nullness checker with the JSpecify semantics, you get the same bytecode. Nothing changes anymore. And the JSpecify standard tells you, okay, where do you look for these marked and unmarked annotations? What is the interpretation for them? But the bytecode doesn't need to encode that anymore. So that's why we have null marked and null unmarked. Methods, classes, packages, module for null marked. For null unmarked, you don't need module because that's the default for module. And yeah, the motivation is that sometimes you want to opt out. You have a tricky class, but you want to say the package is opted in so that if you add something, it's also considered null marked. So why do we like this? You have one canonical build artifact. You can just use the normal Java compiler. You get canonical bytecode without anything happening by the build tool. Each type system is independent. You run your type checker separately. It's not influencing what bytecode you're producing. Disadvantage, you have this extra annotation to explain. We need to motivate. Why do we need null marked? Hopefully I did that now. Why do we have null marked? Why do we want this? And why is it a better model? It allows us this to gradually evolve the Java ecosystem to a world where you have null marked. Source code needs to opt into checking. Otherwise, you might think you're running the nullness checker, but you didn't null mark anything, so you don't get any feedback. So the usability might be, there's this trade-off in usability versus the system model that we wanted to achieve. So hopefully we achieved a good balance. How am I with time? Can I still talk a bit? Okay. So type parameters are a bit tricky. So the only reason why we have non-null is actually type parameters. So I don't have an example here. Maybe I do it in a demo. So for the normal checker framework, where we just assumed that all source code opts in, we also need to make the annotations on type parameter upper bounds explicit. And so if you look at this class T that has an unbounded type parameter T, well, I give the answer away. What do you think is the upper bound for that type Object, for sure object, because we didn't specify a class. But what nullness would you say?
Not null.
Not null? Good, you're in the JSpecify camp already. So the Jacket framework used nullable with the motivation that a T by itself is an unconstrained type parameter. The top type in the nullness hierarchy is nullable object. That's the most general type. Nullable and object is the two top type elements. So the interpretation in the Jacket framework was that it means T extends nullable object. So, and we made that default explicit in the bytecode. Then if you wanted non-null, you could write T extends object. You didn't need to add the non-null on the object because it was in explicit type use. All explicit type uses are non-null by default. So we produce different bytecode. So we produce T extends non-null object. The problem here is with trying to do this with JSpecify is that the bytecode looks exactly the same. Whether you write T or T extends object, you don't see the difference in bytecode. So whether you add the null marked, you wouldn't see anymore whether you had an explicit upper bound extends object or not. And now we had this conundrum. Okay, what should we do? Do we have different annotations whether you write T or T extends object? We don't want that because we cannot tell the difference from bytecode. Or do we suddenly say, okay, even though I have an explicit T extends object, it suddenly meets T extends nullable object, diverting from the default that we say with a null marked annotation. So what we do in JSpecify is that just T means non-null T. On the bytecode side, we don't want to change anything. And on the bytecode side, we cannot tell the difference whether it's just T or T extends object. The bytecode is exactly the same. So we said we interpret it as T extends non-null object. And then whether you wrote the extends object explicitly, it makes sense because you have an object, you're in null marked scope, so it's non-null object. And so this was one of the tricky places where we broke with what the Jacket framework previously did to follow a model that the bytecode doesn't change and we have a consistent interpretation of what the annotation means. So if you want a general type, unconstrained type parameter, you now unfortunately have to write T extends nullable object. So if you just write T, it's not the most general type anymore. You need to write T extends nullable object to make that upper bound more general. Okay. Any questions on basic nullness? Basic JSpecify? Yes?
If these annotations are going to be as the intermediate step for Java to migrate to null safe language, or it is going to be as kind of final destination. I'm asking because I see, for example, so in dark language like in Flutter framework, so they migrated the language to be null safe. So is it going the same for Java or not?
So that is a question to the Java designers. The Java designers have work on value types, and for value types they want nullness information. So eventually Java will hopefully get to a place where they also have nullness information in the language. We are Java 25 now, so who knows at what language level that will be added, and we talked before about Java 8 still being around until the sun dies. So there will be a long window where you need annotations as the transition mechanism. And that's our goal with JSpecify, to be the standardized transition mechanism where you have these nullness annotations. So since Java 8 you can use that mechanism. We had a compiler version that worked for earlier version, but Java 8 is our minimum at the moment. And then Java 30 or whenever we have nullness features, our hope is the transition can be very mechanical. So that wherever you say nullable object, you say object question mark or whatever the syntax will be in Java 30. And so nothing is the final destination. With Java we always have more that we can add.
Have you discussed this question with Java guys?
The Java, what is the value types proposal?
Value types, but exactly your team?
So OpenJDK is aware of the project. So Oracle people, Kevin Brillian, one of the people at Google that worked on this, is now at Oracle. So that team that works on the value types is definitely aware of JSpecify.
Okay.
Yeah.
Would it make sense to have the nullability of a type be parameterized?
To have what?
Like, would it make sense to have the null versus non-nullness of a type itself feel like a type parameter?
So that's a great point. So you should only use these annotations, not just nullness, but everything else. If you don't,
What's the question again?
so whether you should just use a type parameter to encode the nullness of something. So, and for many properties, you can use a nicer class hierarchy. So where you have a tainted string and an untainted string and use separate classes and have a nice class design. Nullness is one of the trickiest properties because it's just so ingrained in anything. So it doesn't really make sense that you have some, well, so we have optional. So I think what you're asking is why don't you use optional maybe?
So what I meant is, like, if you had a method maybe that took a nullable, a non-nullable type string, a non-nullable string, and then you had like maybe you wanted to handle if it's a non-nullable string versus a nullable string. It's almost as if like a type parameter can be an int or a string or anything.
So maybe you mean polynull, maybe you mean something else. So you mean one method that can take either nullable or non-null values?
Yeah, so like maybe if it takes a nullable input, then it would give you a nullable output.
Yeah. So for that, the Checker framework has an annotation that we call polynull. That is, gives you this polymorphism, where you can say you have a method that if it takes a nullable value, return a nullable value. If you take a non-null value, you get a non-null value back. So that is like introducing a method type parameter that only quantifies over the qualifiers. But that doesn't solve the problem. So the solution to the problem might be that you say everything should be non-null and you use optional. So that's an alternative to using qualifiers, is to use optional. But maybe I have these slides. Optional is also very tricky to use. And because for an optional, you can just dereference the optional, and then how do you know whether it's present or not present?
You have to like add another annotation.
We have an optional type checker.
Oh, okay.
And so that optional type checker keeps track of whether the optional is present or maybe present.
But does it keep track of it's a null? Because technically it would be a null.
If you enable that other type system. So you have one type system that keeps track of the nullness, another that keeps track of the presentness of the optional. And then if you make both happy, you have a guarantee that you don't have a null pointer exception and no such element exception. Yeah. Yeah.
Right now, it will be applied to all the reference types, right? Like to objects, to like by default.
So for nullness only makes sense for reference types. Yes. Yeah.
Because I saw like upcoming changes, maybe like it is not Java 25, but maybe next release they want to introduce some changes to how primitives work.
Yeah.
They want
These
to
value
make
types.
Yeah.
Yeah.
So, but they want to make it work with map, like as an objects, like
Yeah.
maybe here you need to also like adjust or to. I'm not sure like how that mechanism will work, but I mean like I'm aware of the changes
Yeah.
they want to introduce, like how the primitives will be referenced.
So I think that's how nullness comes into this value type problem. That you know whether something is value type, it's a value type if it cannot be null. And then if it can be null, you maybe still have a reference type, and then you have some annotation, some question mark, and bang, whatever syntax Java will add to make it explicit.
I mean like that's why we have primitives. We don't want them to be a reference type, right?
Exactly.
Yeah. How they will implement it, I have no idea, but let's not discuss it.
Okay. I can go on talking if you want advanced features, or we can just do examples if you want.
Who wants everything?
Everything. Okay.
Okay,
So I already mentioned flow-sensitive type refinement. For nullness, it should be very obvious why we want that. we have a null check in that then block. We want that reference is non-null. We don't want what we had in Java, that you have to add an extra cast that makes that type change explicit. And we do that in the sound way. And if you know that something is definitely non-null, we refine the type. So every type you have a type check or a type assignment where you know that something is definitely non-null, you refine the type for that scope. So if you assign something where you don't know whether it's nullable, you unrefine the type and it becomes nullable again.
I have a question about that.
Yeah, sure.
Does that appear in the bytecode as well?
So that didn't even appear in the checker framework bytecode.
Okay.
Because there the only thing that you need in the bytecode is the variable type, and the type refinement don't show up in that bytecode.
Okay, yeah. Because I was wondering, because it seems like you need to declare a new local variable.
Yeah.
Yeah.
Yeah, so that is that flows into diff refinement, just happens on the abstract syntax tree where you keep track of the types.
Yeah.
You don't need that in the bytecode.
Okay.
Yeah.
If there are tools available to help with migration for these annotations, like I remember again reference to Dart, yeah, they implemented a migration tool to help to mark. So if you have huge source code repository, so it helps to mark all the source code.
So that is something that still needs some improvement. So error-prone has some suggestions for when something should be nullable. So like it looks at your method body, sees a return null, and then it tells you you probably want the nullable. So there's some support in error-prone that helps you with the migration, but I don't think there's a consistent story yet when to add null marked and things like that. So that's definitely would be useful. Yeah. Maybe IntelliJ has, the IDE has some quick fixes and guides like that. But I'm not sure there's a command line tool that.
I saw just exactly when you're editing a specific file, yeah, they have this. But I saw just only for the specific file, so not all repositories.
I think
Yeah.
you can use open rewrite. If there's no recipe.
True.
Yeah, kind of this, yeah.
Yeah, you can write your own.
True. And Open Rewrite has a JSpecify rule. So yeah, they posted that. So there is some automatic tool. I don't remember what it rewrites, whether it adds null marked automatically. Maybe it adds the null marked for you, something like that. Yeah. Okay, so we do this flow sensitive type refinement, and I just told you I do this null check for the field, and we do that automatically. What if I call a method here? The field was declared nullable. I performed a null check, but that only checks at that instance in time. You invoke a method that can do arbitrary things. It looks at a nullable field, it assigns null to the nullable field. So we cannot rely on that type refinement after some side effecting method. So in our framework, we like to be sound. So we have sound defaults, where we keep track of what side effect different methods have. And by default, we would say method 1 can do arbitrary things, and it was a nullable field, so it can assign null to it again. So we would warn you that my field might be null again in this place. We also provide many mechanisms how you can avoid these problems. We have a very unsound flag to say assume everything is pure, side effect free. That's probably not a good idea, but it gets you going.
So if I understood correctly, so if it's within the same compilation unit, you do track the side effects of the method, and if this method 1 doesn't do any reassignment, you wouldn't issue a warning.
No.
But let's say I pass this
So
to
no.
the third-party method.
Okay.
Like,
If you do what? You pass.
let's say I use a library.
Yeah.
And it's like a black hole. I just pass this to that library. Will you issue a warning saying that potentially my field could?
Yeah. So the goal for the checker framework is to be a modular analysis. So we don't look at the implementation of another method. So let's just, I think it's more fun if we just play around with the code. So here we have a void bar, and we want,
Could you zoom in a little?
can I zoom in? Let's see whether the key works. Is this better?
if JSpecify is going to be part of Java compiler?
No.
No, at all. Yeah, because
So-
for example, we could use, for example, we could reduce null checks, right? If you will mark not null, but indicate, but there is expectation that compiler would verify for these annotations, not null annotations. But in the case if a compiler, but in order to work of checks for these not nulls, we have to add additional parameters to involve plugin for checks. So it would be great. In the case if someone else will not turn on this flag, in this case it is possible to broke the source code report.
So I think the JVM is heavily optimized for null check. So I discussed that once with somebody, and they said that it's so optimized already. The gain that we would get from trusting something that's not under our control would be minimal. So I'm not sure that that would add any performance benefit.
Or in this case, probably project has to specify these checks directly, like in Maven or Gradle. Right?
Well, but then,
Explicitly.
Okay, so here it passed, and now we invoke this bar method. And even though you could say, okay, it's in the same compilation unit and doesn't do anything, we still warn you about it. So let's run the checker. So the zoom factor is a bit annoying. So we still warn that here we have a dereference of nullable.
So regardless of empty body.
Yep. So what is the reason for that? So the reason is that we could have class sub extends demo, and we do void bar that does f is equal to null. So you could have a subclass. The subclass is well typed because it just sets this nullable field to null.
If you mark it final, like
So there are a few things that maybe I don't think we do that. So we wanted a modular analysis where you assume an open world that for some cases we could probably optimize and say, okay, it's a final method, we look at the body and we infer that it's side effect free. So there are a few things that we could do. We said, say, we are consistent, we assume it could contain a side effect. So what can we do? We can do side effect annotations where we say, our purity is trusted at the moment. Okay. So here we if we run in a more conservative mode, you would get a warning here because this method is definitely not pure. So we have this purity annotations where you say this method has no side effects, and then it should complain about this. And then it allows the refinement because you specified that you don't have side effects.
Is it a part of JSpecify?
No. Not yet. So there's always the possibility to add more. So we have the side effect free annotations, we have monotonic nullness, and we have pre and post condition annotations that allow you to specify your behavior. So side effect is whether you have side effects. Deterministic is if you in the same state produce the same results, and pure is the combination of the two. So it allows you to precisely specify what your expected behavior for code is, so that you know what the side effects are, and then what refinements of your types can you keep.
do you check for the actual side effect present?
No, so I just mentioned that it's a trusted annotation because the problem with purity is things like benevolent side effects, like a cache. And you want that the cache can be updated, and externally it's still pure, so it's observationally pure. And so if we implemented a strict check, it would be very hard to use.
I have a question regarding state safety. When you put it as a non-null, so I wonder, how does it work with
Great point. So this refinement on fields, Kotlin doesn't do that because it wanted thread safety. We do it because we said, okay, most of our code that we were interested in was single-threaded. And so we have a flag where you can say, okay, assume concurrency, and then it doesn't do the refinement for fields. Yeah. Okay?
So, like back to polymorphism, if you have a subclass overrides a method and changes one of its parameters from nullable to not null,
Not allowed.
so it'll actually fail the computation, right?
So we want Liskov substitution principle, behavioral subtyping. You can only widen parameters and narrow return types. So you can go from non-null to nullable, that widens your scope for the method, and you can return types from nullable to non-null, but not the other way around. So the other way around would be unsent. Yeah. And there are also some trade-offs with, if you interact with Kotlin code, your parameter should be invariant, because in Kotlin it's invariant. So you have some interoperability problems.
We're actually implementing a flag.
Yeah, exactly. So there is some work on a flag to enable that invariant behavior.
If this checker framework, it doesn't have a feature to refine only changed files.
To do what?
Only changed file by commit. Because in case if you have huge database, so we don't want to break everything. We would like to make it smooth and just only change it file. It doesn't have something out of the box.
So that's not really a checker framework problem. So that's a build system problem. So you should configure your build system that it only compile the things that you want. We're working. Has anyone heard of Sarif? It's the standard static annotation research interchange format. So it's an XML format for static analysis results, and we want to produce output in that format. That even if you produce a recompile, you can look at what the differences are. But this incremental compilation, that's just a build tool issue. I don't think the checker framework needs to do anything there. Okay. Monotonic non-null in lazy initialization. You sometimes have fields that conceptually are non-null, but your constructor doesn't initialize them. So you want something that's lazy, it's still nullable until you are certain that it's non-null. We called it monotonic because once it's non-null, it can never become nullable again. So it's monotonic in that sense. And so you avoid rechecking. You have an initialization method that has as post condition that that field is non-null, and then you never need to recheck as long as you know that that method was called. And yeah, that's these pre and post condition annotations, so you can specify that something is required to be non-null, and you have post conditions to specify what happens as the result of a method invocation. So all of these advanced annotations are not part of JSpecify yet. So these are checker framework annotations that have been very important to make it usable. So if you live more in JetBrains land, there's add contract as an annotation. That has a very similar feel to what we do in pre and post conditions with, in my opinion, a very obscure syntax where you have to write the parameters and arrows and remember how to write the contracts. So I like our language better, and JSpecify wants to do something in this space, and we'll see how fast we get to that. Before we,
I've noticed that IntelliJ has sort of a synthetic contract on a lot of library methods. Is there something in JSpecify or checker framework to say add those types of annotations to like all the standard library methods or some other third party?
Great question. I don't know what IntelliJ uses. Eclipse has the last NP repository where they have specification for the JDK. And with the checker framework, we have a separate clone of the JDK where we added all our different annotations. And JSpecify has another clone of the JDK where we only added JSpecify annotations. And so you have this JDK, and in this JDK you provide your specifications. So here we had some discussion for objects.hash, and should that be allowed or not, and then consistency, this makes sense, and so you add these annotations to the JDK. And it's very nice to do this in a fork of the JDK, because then you see the code, and you just saw he merged upstream, and so you have an easier time than having this last NP format where you have a separate format that you need to maintain somehow. This is not an official part of JSpecify, so this is just for a reference checker. that builds on top of the checker framework. And so we use that same mechanism. Standardizing this, we'll see whether that happens. Yeah. Polynull, I mentioned that idea before, that sometimes you have methods. If it gets something non-null, it returns non-null. If it has some nullable, it returns nullable. So we call that polymorphism. It's method level qualifier polymorphism. So it's very important for certain code like interning.
Isn't it the same like
No?
Like nullable and not null, like and should be nullable, right? Like that's from that perspective.
No. So because for a call, if the method is polynull and you pass a non-null argument, if it's polynull, you know that the returned value is non-null. If it's nullable, it's nullable.
Yeah, but if it is polynull and it can like actually return nullable, right? If it is overriding as a nullable.
It's like the same contract as object.mapping.
Oh, yeah. So it'll be like just map null to next nullable, like to empty, right? If it is empty, match will return empty.
I'm not sure what you mean. So here the idea is that if you pass something that's non-null, you know that the result will be non-null.
No, I mean like we have two methods. One returns not null and one is nullable.
Yeah.
And we have like the polynull, which means like...
So that's the alternative. Instead of two functions, you just need one function.
Oh, got it.
So and that one function behaves like you had these two separate functions. And we don't want that code duplication from having two functions.
Yeah, got it.
I guess a second question there is, imagine one internal and takes one argument, but imagine a function that takes multiple arguments and...
At the call site, you just build the least upper bound of all the arguments.
Okay.
So and then if any one of them is nullable, you get a nullable back. If all of them are non-null, you get non-null back.
Yeah. Like imagine, so one place where I've made functions that behave that way would be parsing a string into a box integer, say. So if you give me a null string, I'll give you a null box integer. If you give me a non-null string, I'll try to parse it into a non-null integer.
Yeah.
But then say maybe there's like a radix argument that for whatever reason is nullable, like a parameter. So that parameter might be null or not null, but it doesn't affect the nullness of the return type.
Yeah, you lost me at some point in the example, but maybe let's discuss that afterwards.
Sure, yeah.
So polynull has only certain places where it's useful. So you can think of it like a method type parameter that only quantifies over the qualifier, not the whole type. Only if the input is null. Yeah. So that's what polynull says. If the input is non-null, you get non-null back. Okay, we have a non-null field. I already mentioned initialization is hard. If this code is somewhere in your constructor and you do it too early, you didn't initialize that field yet, you can still run it to a null pointer exception. So we have a separate type hierarchy for initialization where we keep track of how far along the object initialization is. So we have this frame that keeps track what part of your class is already initialized, and it allows you great flexibility. So you can have helper methods that take a partially initialized object, turn it into a fully initialized object up to a particular frame. So it's a very nice mechanism that by default works without any annotations because most initialization code is very straightforward. But it also allows you to do very tricky things where you have helper methods that take under-initialized objects. So maybe you hear that recommendation that in a constructor you should never call a dynamically bound method, and that's true, but we allow you to specify that method, that it takes an under-initialized object that has to be followed by subtypes again, so you only rely on the pieces that you know. So you can safely invoke a dynamically bound method in a constructor. Okay. Also already mentioned this, maps, even if the key is non-null, if you use a key that's not there, you get a null value. So you will also need to keep track, did you check whether that key is in the map or not? And the nice thing is that you usually don't need to, so we have an annotation, this key for annotation that I showed before, but usually you don't need to write it, because usually you do some iteration, and you know that you iterate over the key set. You have that in that node variable. That node type is refined that it's a key for that map. Then you have that second iteration where you do predecessors that get with that node. And we know node was refined to be from that key set, so we know it's a key into that map. So it very precisely keeps track of what the information flow is to make sure that here we get that value type T back with one extra annotation. We needed for the dominators list that it's a list of key for #1, where the #1 is the parameter itself. So this is again more advanced feature that we don't need, don't standardize in JSpecify. Warning suppressions, I already mentioned that before. Standard nullness, standard suppress warnings annotations. We have special support for assert statements and many other mechanisms to suppress warnings. Command line flags that make it possible to say this package, not usage of this package, declaration from this should have this annotation. So it's very flexible to configure what errors you want to check. External libraries, I already mentioned that. We have that annotated JDK, and we have so-called stub files where you have a text stub where you just specify API for certain methods. So it makes it very easy to provide annotations. Okay, what does the checker give you? It should give you a guarantee about no bugs in your code. We want sound type checkers that give you a guarantee about correctness, and you shouldn't be able to cheat with annotations. So there is some caveat to some annotations we handle in specific ways. For most of them, we have a command line flag to be stricter, like for the purity annotations. So you shouldn't be able to cheat. Caveat, only for code that you type check, that should be obvious. Our tool is an annotation processor for Java source code. So you only type check that source code. If you have native code, if you have some bytecode that you didn't type check, you don't know that. We wanted to type check source code. You can have these warning suppressions. You explicitly told us not to check that code, so you don't get a guarantee for that code. Caveat 2 is that there might be errors in the type checkers. That's why in our theses we have these formalizations and formalize what the type systems do. And if you want, we can go through this too. Who wants to look through this? No? My PhD students wanted to go through it. Come on. So we have these formalizations of the type systems where you have a formal model of a minimal Java, so a small object-oriented language, where you actually have a guarantee about correctness. And so we have a formalization and a sound verification language where you have an actual proof that this is correct. Now that proof is just for a small language, and Java is a very large language.
Do you guys like hand calculate this, or is it like a DSL for this?
So when I did this, my PhD thesis is what by hand. My PhD students now use ROC automated theorem prover, where you formally write it down. ROCQ or QC. Well, COC is the old name. We don't use that name in public. So this is just LaTeX. Yeah, that's just typesetting. So this is pen and paper when computer scientists say it is LaTeX. So this is just math formulas. But now there is a DSL as a proof assistant that helps you to formally prove these properties. Yeah. But you only do this for a core language, not for all of Java. So when we implement it in the checker framework, it's for all of Java, so there can still be, there is some interaction between the language features that you didn't think about formally. That might be unsound in the actual implementation.
So you write your proposal, and then you guys like check it in like the what's the theorem proof?
ROC.
Yeah, that one. Yeah.
ROC. Yeah.
Yeah. And so you first check it on that, and then you go on and start working on the actual Java code for like
Well, it's iterative like many things. You implement your type checker, you prove the soundness of the type checker in parallel. You get some experience with real code, how does it behave, and then you think about, okay, did I miss a qualifier, did I miss a distinction that you need? So you do the thing in parallel usually. Ideally, like everywhere, yeah, you do the formal part first and only that, but usually you need some understanding of your problem domain. And you only get that understanding from the problem domain if you have a type checker. So you do the two things in parallel. Does that make sense? I would love to go through this, but so just as a final slide, verification versus bug finding. So the goal for optional type systems is that it's a... Oh, sorry. For the what? For which part? For the last show. Oh, so this system was an ownership type system before ownership was cool. So it was an ownership type system for Java used for formal verification. So this is from my PhD thesis, is 2009. So this was an ownership type system.
Was it using like a natural reduction or a filtering system?
So this was just a type soundness proof. So it was a formalization. On the left you see the type rules, on the right you see the operational semantics. And then I proved soundness of that type system. But yeah, we can talk more about that type system later. So formal verification and R pluggable type systems are a lightweight formal verification approach. Our goal is that we have a sound type system. We don't want any bugs in the code. If you say there is no null pointer exception, up to the caveats about what parts you type checked, there should be no bugs. For lightweight bug finding tools, you have a different trade-off. You want that you find some bugs at low cost. You give some useful feedback to the user, but you're not too annoying to the user. So there's a different trade-off in what your goal is. For verification, we need to provide specifications. Without specifications, what do you check? You would need to make some assumptions. That's what bug finding tools do. They say, okay, this looks like this was the intent of the programmer, without actually knowing what the actual intent is. So you infer what the likely intent of the code was. False negatives, so saying that the code is correct even though it can run into problems, should be excluded from a verification approach because we want a sound verification approach. For a bug finding tool, it's okay. You trade off how many error messages you give to the user for how sound it is. And so false negatives have to be acceptable. The trade-off are the false positives. If you want to be sound, you over-approximate your knowledge and you exclude things that would actually be sound. So you report errors for code that would actually be correct. And bug finding tools try to avoid that. They don't want false positives. They want to use and not annoy the user and try to focus on high priority, very likely bugs in the code. Downside for verification is the user burden. For bug finding, it's the missed bugs. So neither one is better. They have different application focuses. And have you people heard of error-prone? Yeah. So error-prone is this very lightweight bug finding tool that is very fast, that is enabled on every build, that gives you immediate feedback on things that have a very low false positive rate. It might miss errors. It doesn't have a nullness type system, but it has a few things where it immediately sees here you definitely dereference null. It raises an error for that. And so you have this gradual thing. You have error prone. Everyone can enable that every time. You have spot bugs, a lightweight bug finding tool that sometimes gives useful feedback. And then you have the checker framework, a lightweight type system, and then you have key and OpenGML, more formal design by contract languages that allow you to deductively verify the correctness of a code at even greater detail, even greater than what a type system allows you to do. Okay, so our goal with these type systems is to take the built-in type system, make them both give stronger guarantees and still be practical. So make it as useful as possible to as many people as possible. We have great experience with these tools. Type checking has the nice property that it's familiar to people. Many other formal verification approaches give very confusing error messages, and you usually need a PhD to understand what the error messages mean. Type checking has this nice local modular feedback where you only do local reasoning, and the feedback that you get is much easier to understand. You don't need a whole program analysis. So it's modular, it's fastish. The checker framework is not the fastest tool, but it's a research development tool. So speed would be nice to optimize, but it's faster than many other verification tools. It's incremental, it's built into the Java build system, so you get for the parts that you do. Main concern is annotation overhead. In our experience, it's not so bad. So nullness annotations is the most heavyweight because nullness is just everywhere in Java. So you have maybe one annotation per 75 lines of code. But for many of the other type systems, you have a few hundred annotations for millions of lines of code. And you still find bugs. The thing is, for this format annotation, there are only very few places where you care about the format strings. And every other code gets just type checked with the default. So you handle 2.8 million lines of code with 100 annotations, the few places where you passed around these format strings. You get false positives, but usually it's for poorly designed code. If the logic is easy for you to understand, it's easy for the tool to understand. If it's hard for the tool to understand, it's probably hard for you in a week to understand. So use the feedback from the tool to improve your code quality. Microns performed a study with first-year computer science students, and they preferred using a static analysis tool instead of manually reasoning about the correctness of their code. And yeah, people use it all over the place. There are many companies that incorporate the checker framework and even just parts of the checker framework. So I showed that purity annotation. So we have this data flow framework that provides a data flow analysis for Java source code. And then the checker framework is just a type system on top of that. Then error-prone and null-away, just use that data flow framework because that's a useful abstraction for many other tools. And so even if you don't want the type system, maybe the data flow analysis is already useful for you. Yeah?
Do we have IDE integrations like plugins?
So no explicit plugins, but it's just annotation processors. So in the IDE, as long as you can enable annotation processors, you can run them. We have an LSP daemon. We should finally make a LSP server, so we should just make a release of that. And then if you have an LSP IDE, you should be able to incorporate it. Yeah. Okay? Quick tips. Start by type checking part of your code. Don't enable the 2,000 type systems that we provide on all of your code, and try to understand the thousands of error messages that you get. So focus on a property that's important to you. Focus on a few key classes and type check those classes. Only type check properties that you care. Use subclasses if possible. So nullness is just this pervasive property that's hard to incorporate in your class hierarchy. So maybe I misunderstood your question. You cannot really incorporate nullness in your class hierarchy. For some other properties, you could. You could have a tainted string and an untainted string. The problem is that all existing APIs just support string, and string is final. So the only way that you can support this fine-grained annotations is annotations, where you can have a tainted string, a SQL string versus a not SQL string. Ideally, we don't have stringified APIs where everything is just a string. Hopefully, eventually we get to that where we have value type and have no overhead for doing that. At the moment, annotations are the only way to do it. Write the spec first. If you don't understand what your code is supposed to do and you just try to fixing bugs that come up from the type checker, you're not really improving your code. You're just trying to play catch up and fix your code. First, think about what did you want to achieve? What is the intended behavior? And then add the annotations, run the type checker, interpret the feedback, and see how to change your annotations. Warning suppressions, obviously they add uncertainness, you don't want to do that. And raw types, hopefully, who still uses raw types intentionally? No? No. Okay, good.
Legacy software has them.
Yeah, so that's the problem. The legacy software still has raw types. if we just see list, we don't know. Is it a list of non-null strings or nullable strings? So we again, or maybe there are integers in it. Yeah. So that's the reason why avoid raw types, because they make extended type checking harder because you don't know what's in that list. Okay. So I hopefully convinced you that pluggable type checking is a simple static analysis that you can try and play around with. We have this website, preventing null pointer exceptions at compile time is the easiest of the type systems, even though it's the hardest type system. Many of the other properties are easier. So if you have some other property that you might want to enforce, see whether a lightweight type system might be good for you. And yeah, you have nothing to lose other than your bugs. So try static analysis. And the other thing, JSpecify, if you have nullness annotations in your code, get rid of 3 or 5, see whether you can standardize on JSpecify. It will make your life easier. The package that JSpecify uses is jspecify.org, but for some obscure reason, the website is jspecify.dev. jspecify.org redirects to it, but not on HTTPS. So that's why you see 2 URLs there. Eventually, it might get fixed. And yeah, if you're interested in other properties, we have a list of what the topics are that we explore next. So check return value was the next one, and then maybe immutability and a few other properties. But we have about a dozen proposals of what we should look at next. And yeah, if you have any questions that I didn't answer, I'll be around here. Billy and Alex will be here, and file issues on our GitHub page.
All right.
Thanks.